Okay, this one is a case of ANOVA. So our null hypothesis is that the mean from limestone is the same as the mean from granite, which is the same as the mean from shale. The alternative hypothesis is that at least one of those three means is different from the others, the population means. So what we're going to do is we're going to look at comparing those means, and the way we're going to do it, remember, is by comparing variances. We're going to look at two estimations of variance, one based on the means, and then one based on the average of these three numbers. Since the sample sizes are the same, we can get away with this, and this is the only way that we'll look at this from a mathematical standpoint. So this is based on some pretty clever trick. If you remember that the standard deviation of the population divided by the square root of n is equal to the standard deviation of x bar. Well, we can play around with that a little bit. We can say that the standard deviation divided by n, or sorry, the standard deviation squared divided by n is equal to the standard deviation of x bar squared. And then we can say that the standard deviation of the population squared is equal to n times the standard deviation of x bar squared. Well, we use this trick by saying we're going to let this thing be estimated one time at least by this thing. We're going to let the standard deviation of these three x bars times n, which in this case would be 15, we're going to let that be an estimate for s squared. So that's one way we're going to look at the standard deviation of the population. The other one will be the average of 0.65, 0.57, and 0.64. So we're going to estimate the standard deviation of the entire population. The whole thing is based on the idea that we're going to just lump all of these things into one population because our null hypothesis says that the means are all the same. So we'll look at the variance from this perspective, then we'll look at the variance from the other perspective. So let's go to it. I've already put those things into my calculator. I'll clear this out. If we hit stat and we look at list 1, you see them all in there. We'll go like this. Statistics, calculate one variable statistics for list 1. And notice that the standard deviation here is 0.357. That's the standard deviation of the means. So the standard deviation of the means is equal to 0.35. Let's keep it a little bit more accurate. 763. So n times s of x bar squared, our estimation for the variance based on n times x bar s of x bar squared is going to be equal to, let's quit that, 15 times 0.35763 squared, n times s bar squared. So we get 1.9185. That's one of our estimations for the standard deviation of the underlying population, of a pooled population. The other one is just going to be the average of those three numbers, 0.65 plus 0.57 plus 0.64. And I'll take that and divide it by 3. The other estimation is the average of the three standard deviations, and that works out to be 0.62. So the average of the standard deviations is equal to 0.62. This looks like a lot more than that. So remember, that's some evidence that we have something that looks like this, where the variance between the means is a lot more than the variance within the populations themselves. Let's see if that's big enough. So what we're going to use is a whole different statistic. We call it f. And F is just going to be the top divided by 0.62. So 1.9185 divided by 0.62. Basically, we're saying that this estimation is a little bit more than 3 times bigger than this estimation. I'll write it correctly, 3.09. This estimation is a little bit more than 3 times bigger. Is that bigger enough to be able to reject the null hypothesis? To be able to find that out, we need to look at a new test statistic, F. Table A5 in the back of your book. There's one table with 0.25 in the right tail. On the next page, there's another one with 0.05 in the right tail. This is the one we will be using as a default. The numerator degrees of freedom, since there were 3 different x bars, there are 2 degrees of freedom in the numerator. Since each of our standard deviations was based on a sample size of 15, each of these standard deviations was based on a sample size of 15, there are 14 degrees of freedom in the denominator. So 3.73 times bigger would be big enough to reject the null hypothesis. The numerator degrees of freedom is 2, the denominator degrees of freedom is 14. So our critical value, CV, was equal to 3.17. What that means is the F statistic looks kind of like this. Our test statistic was here. Our critical value was here. The rejection region is the region out here, where this area is 5%. So we have to fail to reject the null hypothesis. There's not quite enough evidence to show that the pHs for these different rocks is actually different. The way we could get more evidence, we could make this number larger. Making this number larger makes this larger, which makes this larger, which makes this one bigger compared to this one. All right, thanks very much. Hope that helps.